Yesterday, we started talking about derivatives and graphs. We really want to start using our first derivative, and this is one of our classic problems that we use the first derivative for. The first derivative of a function tells us about the direction of the function. The sign of the first derivative tells us about the direction of the function. Sign of the first derivative. Tells us the direction of the function. The sign of the first derivative tells us about the direction of the function. Sign of the first derivative tells us about the direction of the function. What we saw yesterday is that if the function is increasing, then the first derivative will be positive. If the function is increasing at a point or on an interval, then the first derivative will be positive at that point or on that interval. So if f is increasing, then the first derivative is positive. Function is increasing, then the first derivative is positive. If the function is flat, then our first derivative is 0. And if the function is decreasing, then our first derivative is negative. And I kept referring to f prime not as just f prime. I kept referring to it as the first derivative rather than just the derivative. Calling it first derivative heavily implies that I'm going to be talking about a second derivative. Unsurprisingly, second day, second derivative. The second derivative is just the first derivative of the first derivative. That is kind of a fucked up sentence, but there it is. The second derivative is just the first derivative of the first derivative. So the second derivative of the function is the first derivative of the first derivative. It tells us the same thing. If the first derivative is increasing, the second derivative will be positive. So if the first derivative is increasing, then the second, I don't know if I want the first derivative to be orange the whole time, or if I want direction and sign to be the same color. I'm going to try it this way. If the first derivative, f prime, is increasing, that means the second derivative, which we use the stunningly original notation f double prime, if the first derivative is increasing, the second derivative is positive.
Double prime is the second derivative.
Double prime is the second derivative. So this symbol here, f double prime, we say f double prime. We write f double prime, we say f double prime, we mean the second derivative. We write f double prime, we say f double prime, we mean second derivative. The second derivative is just the first derivative of the first derivative. I'm just going to say the derivative of the first derivative, so I'm not saying first all over the place. So we say, or we write f double prime, we say f double prime we mean the second derivative. Specifically, the second derivative of f. The second derivative of f is the derivative of f prime. The second derivative of f is the derivative of f prime. So whatever the first derivative tells us about the function, the second derivative tells us about the first derivative. That's why I'm just going to take this stuff and move it over one derivative. If the first derivative is flat, then the second derivative will equal 0. And if the first derivative is decreasing, then the second derivative will be negative. And these are all if and only if statements. If the function is increasing, then the first derivative is positive. If the first derivative is positive, then the function is increasing. Whatever we do to find derivatives, that's what we do to find the second derivative. So for example, if f of x is 2x to the third, then f prime of x is 6x squared. We just do nx to the n minus 1. If I want the second derivative, I just do the same thing, another nx to the n minus 1. Whatever the first derivative is telling us about the function, the second derivative is telling us about the first derivative. The first derivative is the instantaneous rate of change of the function. So the second derivative is the instantaneous rate of change of the first derivative. So if the sign of the second derivative tells us about the direction of the first derivative, we want to fill in what the direction of the first derivative tells us about the function. That's the thing we want to talk about today. I'm just going to write it down. Let's just jump right to the conclusion. If the first derivative is increasing, we say that the function is concave up. If the first derivative is increasing, we say that the function is concave up. If the first derivative is decreasing, then we say the function is concave down. And these are, once again, if and only if statements. Notice that we left off that the line in the middle where the second derivative is equal to 0. That is, the first derivative is flat. This is where we find there might be an inflection point. Maybe inflection point. And I haven't defined what an inflection point is. An inflection point is a place where a function is changing concavity. That's not a very good description right now. I haven't even told you what concavity is, except for the fact that if it's concave, a function is concave up, that means its first derivative is increasing. And kind of went like this with my hand. It doesn't work on the radio. So people at home, I went like this with my hand. See, I did it again. Some things don't work on the radio. An inflection point just means the function is changing concavity. This is similar when we talk about the function being flat. We might have a local maximum or a local minimum, but it might be neither. It just means that the function is flat. When the first derivative is equal to 0, we call that a critical point. And we say that this is a place where we might have a local maximum or a local minimum or just a flat point. But inflection point is where we are specifically changing concavity. We are familiar with the concept of inflection points. We do use the word inflection point in our kind of normal language. It's very dangerous. Most people don't know calculus, so they don't really know about inflection points. So it's definitely going to be abused because it sounds like a fancy thing. An inflection point just means we're not necessarily changing direction. We're changing concavity. We're changing how things are bent. We do have like we're still working on like a 3-year example with a good idea about an inflection point, because we just went through a big pandemic. The number of infections, COVID infections, can only increase. The number of active infections, that's different, because sometimes that makes things decrease. But the number of people that have been infected by COVID can only increase. In the beginning, when things are spreading fast, the rate of infection is also increasing. The number of infections is increasing. The rate of infection is increasing. So as an example of concavity and inflection points, we want to think about COVID. In the beginning, the number of infections is increasing. So here, this represents the number of infections increasing, and the rates at which those infections are increasing is also increasing. The number of infections is increasing, and the rate of infection is also increasing. All of a sudden, I turned into a stereotypical villain. The number of infections is increasing, and the rate of infections is increasing. Stop being so cartoonishly villainous. The rate of infections is increasing. We see the rate of infections increasing because the slope is getting steeper. The slope of the tangent line is larger as we move along. That's concave up. So since the rate of infections is increasing, that means that the second derivative is positive, so the function is concave up. At a certain point, we get to what's called an inflection point. At the inflection point, the number of infections is still going to be increasing, but the rate of infection will start to decrease. So hopefully at a certain point, we get to an inflection point. After the inflection point, the number of infections is still increasing. But now that the function is bent down, because the rate of infection is decreasing. So after the inflection point, the number of infections is increasing. But the rate of infections is decreasing. That's concavity. It's what's happening to the rate of change. It's how the rate of change is changing. Once the rate of change of infections is decreasing, we say that the number of infections, that function is concave down. The number of infections is still rising, but it's increasing at a decreasing rate. The rate of infection is slowing down. Before the inflection point, the rate of infection is speeding up. After the inflection point, the rate of infection is slowing down. So here's an example of what concavity and inflection are. So at an inflection point, the function isn't changing direction, necessarily changing direction, but it is changing concavity. Something has happened in the first derivative. Something has happened to the rate of change. Any questions? I have an example, but I don't want to do the example. I want y'all to do the example. Thank you. So we're going to start with the easiest one. I want you to think about this function. F of x is x cubed minus 3x squared minus 9x plus 27. A couple days ago, I asked you to think about what could a cubic function with real coefficients look like. Here's an example of a cubic function with real coefficients. I want you to think about what it looks like. We're going to analyze this by looking at where the function is increasing and decreasing. And we're going to find where it's increasing and decreasing by looking at the critical points. So in part A, it says find the critical points of f. That is, I want you to solve f prime of x equal to 0. Take the first derivative of the function, set it equal 0, and solve. Then I want you to figure out whether we're dealing with a local maximum, a local minimum, or neither of those at each of the critical points. It's important to note that we don't have to go into this problem blind. We can not have Desmos ready. So we get y equals x cubed minus 3x squared minus 9x plus 27. So that's not a very good view. So we can see all these points. These are the points that we're talking about in part C, where I ask you to sketch the graph. The critical points are where the function is changing direction. The inflection points are where the function is changing concavity. It's kind of hard to see, but here's the function is concave down. And then at some point with the function changes to concave up, but it's hard to see where. And I don't think Desmos allows you to find that. Desmos doesn't like just stop at inflection points. So you're gonna have to figure something out to figure out where the inflection point is. Where is this changing concavity? Let's quickly run through the calculations. Note that you don't need a whole ass computer to look at Desmos. You can look at Desmos through any browser. You can also grab the Desmos app for your phone. It is free, so just download it. It is a better graphing calculator than your graphing calculator. Your graphing calculator is still a useful tool. Y'all are going to be in linear algebra eventually. It's really good at finding the reduced or echelon form of a matrix. better than any tool that you'll find through a browser. So it's important to have both tools. All right. So we know what this function looks like. This is going to help us classify things. And we're going to get into more detail about classifying critical points and determining if inflection points are in fact inflection points. The big idea is we're going to take the derivative, set it equal to 0 and solve, and then we're going to take the second derivative, set it equal to 0 and solve. And this is going to tell us the location of where things might be happening on our function. First of all, some classic problems, some pre-calculus style problems. If we have a function, we want the y-intercepts and the x-intercepts. The y-intercept happens when x is 0. The x-intercept happens when y equals 0. Here's the other reason I picked polynomial. This one happens to be factorable by grouping. I'm going to use the fact that you've had this skewed view of the polynomial world that things are factorable most of the time, when that's just not true. The probability of a polynomial chosen at random being factorable is 0. When I give you all these factorable polynomials, it's because they were designed to be, I have to go out and pick them. I can't just grab them at random because I don't pick factorable ones. That's beside the point. This one is factorable. We find that there are 2 zeros. The function has a 0 at -3 and a 0 at 3. One of the reasons that I picked this particular example is that x minus 3 is a double factor. It's a squared factor in the polynomial. That means we will think of 3, 0 as a double 0. It happens twice. It has multiplicity 2. 3 is a 0 of f with multiplicity 2. 3, x equals 3 is a 0 of the polynomial f with multiplicity 2. The factor that leads to 3 is a squared factor. So we say that the 0 has multiplicity 2. That's just what we can determine from the function. That is pre-calculus knowledge. Not the class, like that's knowledge we had walking into calculus. In calculus, we learned about the derivative, and that critical points happen when the first derivative is 0 or the first derivative is undefined. That's not going to be an issue here. The first derivative is this quadratic, 3x squared minus 6x minus 9. We set that equal to 0 and solve, and we get 2 zeros for f prime. So we'd say that f, the critical points are a thing that belongs to f. So I would say f has critical points at -1 and 3. If I plug -1 and 3, so I'm saying at -1 and 3. So I'm just giving the x coordinates, the location. If we want to list them as critical points, we could plug the -1 and 3 into the function by hand like I did it here, or by hand by using my hand to press on the calculator buttons and find out where they are. So we could also say f has critical points -132 and 3, 0. I want to make sure that the critical points are a thing that belong to f, not f prime. We used f prime to find them, but the critical points are a thing for f. If we want to find possible inflection points, we just repeat this process. We look for the critical points of the first derivative. So I took the second derivative, it's 6x minus 6, so there's a possible inflection point when f double prime equals 0. So when f double prime equals 0, we get 1, x equals 1. There's a possible inflection point at 1/16. 16 we got just by plugging 1 into the function, either by hand like this or by hand using your hand to press buttons on your calculating machine. I had to put a vertical line at x equals 1 because Desmos does not naturally point out where your inflection points are. questions? As far as classifying all these things, determining whether we have a local minimum or a local maximum or neither at a given critical point, and also determining whether our inflection point is in fact an inflection point, we can do that because we know what the graph looks like. It looks like we have a local maximum at -132 and a local minimum at 30. Also based on the graph, it's an inflection point at 116. Because we can see clearly that the function is concave down before 1 and then concave up after 1. Just looking at the graph, it's really hard to determine where that critical point is. But looking at the graph, but once we find the second derivative, where the second derivative is equal to 0, we say, yeah, that is a critical point. Sorry, that is an inflection point. Any questions? Yes. It won't exactly be the middle because 1 is cheated towards the 3. So halfway between -3 and 3 would be at 0. And this one's pushed a little towards the 3. If there is one, it will be between if we have a local maximum and a local minimum. So that is correct, but not exactly between. Any questions? How's everybody okay? Has everybody downloaded Desmos app on their phone? I really kind of have to update my thinking because I know a lot of people are communicating. School is based on, is really kind of laptop focused because it's designed by old people like Gen Xers and a lot of millennials who like grew up having laptop. I actually grew up having desktop be the computer. And then we're like, oh, wow, laptops are things that we can carry around with us, right? And I think a lot of students today still have laptops, but a lot of students today don't have laptops because we're transitioning away from that towards tablets. And so we're in this really weird place where we have to make sure that our shit is readable on fucking phones because there are people out there writing essays on their phone. And life is strange. School life is weird. So, yeah, grab the Desmos app, play around with this, being able to find these points. The tricky thing is you have to actually tap on the points. And I have big old person fingers, so I'm like, oh, where do I push the button? Man, back in my day, we just had to draw stuff by hand on stone tablets. I'm just kidding. We had paper back in my day. But here's a fun fact. I don't know if you're taking like introduction to computer programming. I don't know what language you would learn these days. The last time I learned a computer language, it was Fortran 77. Does anybody even recognize that? The 77 does stand for the fucking year. So, yeah. Anyway, I'm shitty at computers is what I'm saying. Any questions? Comments? Snapper box? All right, that's it for today. That's it for this week. I will see you all on Monday. Everybody have a good weekend, and thanks for playing. Sign in on the sign-in sheet if you have not done so. Please.